Good day. For those of you who don't know us, we're the instructional staff for ECE 150, professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to begin by investigating recursive mathematical functions. Alright, so in this topic, we are going to examine and implement recursive mathematical formulas. This includes the factorial function, the binomial coefficients, the Fibonacci numbers, and the calculation of x to the n for an integer exponent. Now, from secondary school, you know that the factorial function can be defined recursively. For example, n factorial is defined as being 1 if n is equal to 0 or 1, whereas n factorial for larger values of n could be defined as n times n minus 1 factorial. So for example, 6 factorial can be calculated as 6 times 5 factorial. Well, what's the value of 5 factorial? Well, 5 factorial is 5 times 4 factorial. Well, what's that? Well, 4 factorial is 4 times 3 factorial, and so on and so forth until you calculate 2 factorial, which is 2 times 1 factorial. Now, 1 factorial is the base case, or one of the two base cases, and 1 factorial is equal to 1. Okay, this is something we can implement recursively. So let's do this for the factorial function. So here is the function body, and we will begin by dealing with the base case. Now, since n is an unsigned integer, we don't have to worry about negative values of the parameter. So, if n is less than or equal to 1, we just return 1. Now we have to deal with the recursive case. So, if n is not less than or equal to 1, then n is greater than or equal to 2. So what we will do is we will calculate the recursive expression. So to calculate n factorial, we have to calculate factorial of n minus 1. So that is our simpler result. Having calculated that, we will then return n times that simpler result. Alright, that's it. This is a recursive implementation of the factorial function. Now, in this case, we actually assigned the simpler result to a local variable and then calculated n times that simpler result. If you wanted to, you could also just calculate n times factorial of n minus 1. Both of these would be equally correct, and both of these calculate the factorial recursively. Now, from secondary school, you also know that the binomial coefficients can be defined recursively. So you know that n choose k is equal to 0 if k is greater than or equal to n, and it's also 0 if k is less than 0. After all, there are no ways of choosing 11 things given 10 unique objects. Similarly, there's no way of choosing -3 objects out of 10 unique objects. If k is equal to 0 or k is equal to n, then n choose k is equal to 1. Given 10 unique objects, there's only one way to choose none of them. And similarly, given 10 unique objects, there's only one way to choose 10 objects out of that collection. That is, to choose all 10 of them. However, n choose k otherwise is calculated as n minus 1 choose k plus n minus 1 choose k minus 1. Now, why is that? Well, suppose we have 10 choose 6. So how many ways can you choose 6 things out of 10 unique objects? Well, let's take those 10 unique objects and let's exclude one. Now we're left with 9 objects. How many different ways can I choose 6 objects out of 9 unique objects? Well, 9 choose 6. Similarly, if I've chosen 5 objects out of 9, I can then add that extra one I set aside to that set of 5, and that gives me 6 objects chosen. So the alternative is to, out of 9 objects, choose 5, and then to that set of 5 objects I've chosen, add that extra one I've set aside. So n choose k is the same as n minus 1 choose k plus n minus 1 choose k minus 1. Again, this is something we can implement in C++. So let's begin. So here is our function definition. Now, we have 2 base cases, and because all of our arguments are unsigned, we don't have to worry about the case when k is negative. So if k is greater than n, I just return 0. Else, if k is equal to 0 or k is equal to n, we have the other base case, in which case we return 1. So now we have to deal with the recursive case. All right, so n choose k is the sum of n minus 1 choose k. Well, we can calculate n minus 1 choose k by calculating the binomial function with the first argument being n minus 1, the second argument being k. I can also calculate the other recursive call, which is just with the arguments n minus 1 and k minus 1. Having calculated both of these simpler expressions, I can then calculate and return the sum of these two. All right, so this would be the calculation of the binomial coefficients using a recursive definition. Now again, some of you may have noticed, instead of calculating result 1 and result 2 separately, instead I can just return the one result plus the other result. Both of these are equally correct implementations of a recursive definition of the binomial coefficients. Now, another recursively defined number that you've seen in secondary school are the Fibonacci numbers. So the Fibonacci number for 0 is 0, the Fibonacci number for 1 is 1, and then for any larger Fibonacci number is the sum of the two previous Fibonacci numbers. All right, this doesn't sound that different from the binomial coefficients, so it should be quite straightforward to implement. So here's our function body, and we are going to deal with the 2 base cases. So if n is equal to 0, we return 0. If n is equal to 1, we return 1. Now we have to deal with the recursive case, which is only called when n is greater than or equal to 2. Well, to calculate the Fibonacci number when n is for a given n, we must calculate the Fibonacci number for n minus 1, and we must also calculate the Fibonacci number for n minus 2, and given these two results, we have to add them together. That is the value that must be returned. All right, not so different from the binomial coefficients. And as with the binomial coefficients, we could have replaced the recursive case with a single return statement that calculates the two previous values. All right, so this is a recursive implementation of the Fibonacci numbers. All right, the previous slide saw a recursive implementation of the Fibonacci numbers. Here's a different implementation. So what are we doing here? We start with an array of capacity 2 initialized with the values 0 and 1. By the way, you don't have to be able to come up with this algorithm yourself. This is an interesting alternative implementation of the Fibonacci numbers, and why we're presenting this will become clear on the next slide. Just enjoy this and see this as an interesting way of using coding. All right, so here's that initial array, and if n is equal to 0 or 1, you'll notice that the loop starts at k initialized with a value of 2, and so if n is equal to 0 or 1, the loop body never runs. Instead, we just either return entry 0 or entry 1 respectively out of that array, which are the first two Fibonacci numbers. However, if we have a larger value of n, then we're going to iterate this loop body. And you'll notice that this loop body, starting with k is equal to 2, updates one of the two entries of the array with the sum of the current values in the array. All right, we'll see how that works, and then we return one of the two entries. So this approach is said to be iterative because we are iterating the body of that for loop. That is, we are performing the calculation of the body of that for loop n-1 times. So let's see how that works out. So when k is equal to 2, 2 mod 2 is 0, so I will sum the two values together, which is 1, and save that into entry 0. All right, next, k is equal to 3. 1 plus 1 is 2, and that will be stored in the cell or entry with index 3 mod 2, which is 1, so that will be stored in the other entry. So 2 will be stored at index 1. The sum of those two is 3, and that will be stored in index 0. 3 plus 2 is 5, and that will be stored in index 1. 3 plus 5 is 8, which will be stored in index 0. 8 plus 5 will be stored in index 1, which is 13. 13 plus 8 is 21, which will be stored in index 0. 13 plus 21 is 34, which will be stored in index 1. 34 plus 21 is 55, which will be stored in index 0. 55 plus 34 is 89, which will be stored at index 1. 89 plus 55 is 144, which will be stored in index 0. Well, at this point, k is equal to 12. And the reason that 144 was stored in index 0 is because 12 mod 2 is equal to 0. Well, now the for loop completes because after this k is assigned the value 13, which is greater than the value 12, so the loop stops and we return the entry in 12 mod 2, which is entry 0. So we return the value 144, which is the 12th Fibonacci number. Nice, that's actually quite quick. All right, now if we were to author a program that simply calculated the first 47 Fibonacci numbers in order, we would have the following times it takes to calculate these 48 different values. If we were to do this with the recursive implementation, you may be surprised to find that it takes 109 seconds. Now you may be thinking I have a very slow computer, but that's not the case, because in that second iterative implementation, it took only 15 milliseconds. That is almost 4 orders of magnitude faster than the recursive implementation. So recursive implementations may not always be the most ideal solution, and in your second year course on algorithms, you're going to understand why this is a slow implementation, and you will learn about something called dynamic programming or memoization. Dynamic programming, or memoization as it's also known, is another algorithm design technique that can significantly improve the runtime of recursive implementations. All right, that's something that you have to look forward to in your second year, but we don't have to worry about this anymore. For your own personal enjoyment, mathematicians have come up with an alternative recursive definition of the Fibonacci numbers. This is beyond. Now, here we have a reasonably straightforward recursive definition of calculating x to the n when n is an integer. As you can see with the recursive component, it looks very similar to that of the factorial function. X to the 5 is found by multiplying x to the 4 by the value x. The only subtle difference is, how do we calculate x to the negative 10? Well, what you do is you calculate x to the 10 and you take the reciprocal of that. Okay, that's quite straightforward too. So this sort of function can be implemented very easily in C++, and as we have already done so with the factorial function, we're just going to present this solution. Now, if I wanted to use this function to calculate, say, x to the 100, I would have to calculate x to the 99, which would require me to calculate x to the 98, which would require me to calculate x to the 97, and so on and so forth, all the way down until I calculate x squared, which is found by multiplying x to the 1 by x, and x to the 1 is found by multiplying x to the 0 by x. So essentially I have to recursively call this function 100 times. Okay. Now consider this alternative recursive definition for calculating x to the n. So this looks a little bit more confusing. The first two look the same, but the latter two are a little different. What the latter two are saying is, if, for example, I'm calculating x to the 50, what I have to do is I have to calculate x to the 25, and having found that result, I just square that result. Because after all, x to the 25 all squared is x to the 25 times 2, or x to the 50. Alternatively, if I'm calculating x to the 73, well, I can find x to the 73 by calculating x to the 36, squaring that result, which gives me x to the 72, and multiplying that by x to get me x to the 73. All right, let's implement this function. Again, it should be reasonably straightforward. I have the function body. I have the first base case. Well, actually, this is the only base case. When n is equal to 0, I just return 1. Now, if n is negative, I will just calculate 1 over x to the negative n. And so I'm just recursively calling the function. So if n is negative 10, I will now call the same function but with the argument 10. All right, so the alternative now is where n is going to be positive. So if n is even, that is, if the remainder when n divided by 2 is 0, then I'm going to calculate x to the n divided by 2 and assign that to result. And then I will return result times result, or whatever that is, I will return that value squared. Alternatively, the only other case now is that n is greater than 0 and odd. So, as before, I will calculate x to the n divided by 2, and remember, we're using integer division here, so if n is odd and it is divided by 2, the fractional part is thrown away. So 5 divided by 2 will give me the value 2, not 2.5. Anyway, in this case, I calculate x to the integer division of n divided by 2, and then I return x times that result squared. Now, in the previous implementation, if I wanted to calculate x to the 100, I'd have to calculate x times, I'd have to multiply something by x 100 times, which is going to be very expensive. Here, on the other hand, to calculate x to the 100, I have to calculate x to the 50. To calculate x to the 50, I need to calculate x to the 25 and square that. To calculate x to the 25, I have to calculate x to the 12, square that, and multiply the result by x. To calculate x to the 12, I have to calculate x to the 6 and square that, and so on and so forth. And so, as you can see, there's a lot less work involved here. In fact, the amount of work here is more or less the same that's required for a binomial search. So in the previous version of calculating the power, it was more like a linear search, whereas here it is closer to a binary search. So if I wanted to calculate x to the n, this will actually only require approximately log base 2 of n multiplications, which is a lot more cheap than having to calculate n multiplications. All right, so now we've seen two different implementations of two different recursive definitions of performing the same calculation. And at least we have argued that one of these implementations is significantly faster than the other. Thus, it's not appropriate to just blindly implement any recursive definition that you first find. It's always important to investigate a little bit further. Again, you don't have to memorize this recursive formula for calculating powers of n. But if I was to give you this recursive definition, you should be able to implement this. Now, beyond the scope of this course, but something that may pique your interest, in the previous slide we calculated x to the n divided by 2 and assigned that to a local variable and then multiplied that local variable by itself. What happens instead to the efficiency if we were to call the power function twice? So again, that's beyond the scope of this course, but if you're interested, try it out and see which implementation is more efficient, this implementation or the previous one, and try to determine why. So, following this topic, you now understand the recursive definition and implementation of the factorial function and the binomial coefficients. You understand that the naive recursive definition of the Fibonacci numbers actually translates very poorly to an implementation, We also saw an iterative variation of calculating the Fibonacci's numbers that is much more efficient. You have, however, been exposed to a much more efficient recursive definition of the Fibonacci numbers, and you are welcome to try to implement this on your own. You also realize that there are many different recursive definitions of perhaps the same operation, in this case, we saw there were two different recursive definitions of calculating x to the n, one being much more efficient than the other. Consequently, you understand that different implementations will have different efficiencies and that you shouldn't always necessarily implement what you see first. In the next topic, we will look at recursive implementations of functions on arrays. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!